Hello, welcome to this lecture video. So our purpose is to test, or rather to find what appropriate test and we use to answer this particular question. So what is our problem? So our problem is to answer, is there a significant difference in the average BMI of the students when grouped by their birth rank? So this is our problem. So we want to know if there is a significant difference between the BMI and the average of the students when grouped by their birth rank. Now, of course, we have to see first what are the characteristics of our, or rather, what is the nature of our problem. Our problem is a comparison. So it's a comparison. And possible tests that we can use is the test for independent samples or one-way ANOVA. This is, of course, if our result is what do you call this? If we satisfy the conditions of parametric tests, because these are parametric tests. Now, we do not yet know what is the particular test that we can use here, because we do not have any idea about the grouping or the categories in the bird rank. So which means we have to go and see what is our data all about. So let us see what is the nature of our data. So this is our data. So looking at our data, RS is relationship status, BO is a birth order. So birth order, so let us check if we have some classifications here, but we can see that there are several numbers like 1, 2, 3, 4, 5, and we cannot find for a values for this. So which means, of course, let's just check first if how so initially this is how it looks like. So let's place the birth order and click OK. So we can see in our table that we have 15 first born child or only child, 9 second, 5 third, 3 fourth, 5 fifth, 2 sixth child is 1. If we will be using inferential statistics, our frequency for each category so the frequency for each category must be at least 5. So we see here that it's okay for first child, it's okay for second child, it's okay for third child, but when we reach this part, it is less than 5. So to do something about it, or to have some of course to still use this data. So instead of course disregarding the fourth, the fifth, and the sixth, we can still utilize this. Anyway, we can come up with an interval or bracket. Say for example, 1 is first child, 2 is second child, 3 is third child, fourth is 4 to 4 and above. So here, if we add 3 plus 2 plus 1, of course, this will be 6. And if we can do that, if we combine 4 to 6, then it means that we can already proceed to our inferential problem. So how are we going to do that? So let us first decide if we will be using one. So one can stand alone. So first child or only child, and then second child. And then for three, maybe we can combine three third, or at least rather, at least third child. So we will be combining 3 to 6 instead. Or you can still have more data like first child, second child, third child, at least fourth child. So of course we know what it means when we say it's at least third child. So it means it can be third, fourth, fifth, and above. So how to do it? We have, of course, to go to our data. Let's see our data first. Okay. So we can use the function that recoding, or we can also simply sort this. So let's have another category, BO2. So BO2 is the birth rank. It's a birth order 2. So our second data. So we have to place that 1 means first or only child. 2 means second child. 3 means at least third child. So we can do recoding, or if not, we can also simply sort this ascending, and then of course we can copy the first, second until third. So we can copy this because of course 1 is still 1, 2 is still 2, 3 is still 3. But for fourth, fifth, and sixth, this will be coded as 3. So which means it is at least third child. So next, we are already done classifying or identifying. So let's go back to our board. So we are already done classifying what is the category. So we are already sure. Remember that our problem is comparison. So we know that it is a comparison, but we are not yet sure if it is only two groups or three or more. So since we have 1 for first child, 2 for second child, 3 for at least third child, then this is 3 or more, telling us that possible test is one-way ANOVA. But if we will be using one-way ANOVA, even if of course our BMI data is already at least interval, we still need to check if our data is normally distributed. So our next objective is to check if our data is normally distributed before we will be deciding that the appropriate test, and before we can be assured that our test is one-way ANOVA. Okay, let's go back here. So analyzed. So to check, analyze, descriptive, and explore. So of course, let's reset this first. So BMI, and remember that we will be using the second birth order. So this second one. So of course, we did not classify, but this is an ordinal data. It's not a numerical. And then for plots, we will check normality plots with this. Continue and okay. Let's see what do we have here? Of course, as mentioned in the previous video, you can see other result, but we will just focus on this test. Now, we already mentioned in a separate video that in Shapiro week, we use Shapiro week when we have less than 50 number of respondents. So in this result, n is of course less than 50, 15 is less than 50, 9 is less than 50, and 11 is less than 50. So if P is greater than or equal to 0.05, it means that the data is normally distributed because we are accepting HO. And HO here is the data is normally, the data is normal or normally distributed. So P is greater than 0.05, 0.680 is greater than 0.05, 0.243 is greater than 0.05, which means this is normal, normal, and normal. So in case that one of our data is not normally distributed, we cannot proceed with using one-way ANOVA. So definitely using Shapiro week, we were able to know that the data is normally distributed. Then we are now sure that the test that we will be using is one-way ANOVA. Or ANOVA stands for analysis of the variance. So let's again clear our drawing. So let's do the test now. So what to do? Click Analyze, Compare Means, One-Way ANOVA. So we will be placing our BMI. And then for birth order, we will be placing birth order here. And let's see the options. Let's check descriptive homogeneity of variance test. So this is the Levene's test and Brown Forsythe. So click continue and okay. So let's see what is the result. So as we can see, we have the following result similar to the result of other inferential tests. We have the mean, standard deviation, and the standard error. But our concern again is to see if we satisfy the condition of test of homogeneity of variances or equal variances. So this is our P. So we mentioned again that in the using this test, our HO is telling us that we have equal variances assumed. So since P is less than 0.05, we are rejecting our HO. And this means that we are telling that equal variances not assumed. In the using one-way ANOVA, if equal variances assumed, it means that we will be reporting the result of ANOVA. And in case that equal variances is not assumed, we will be reporting the result of the Brown-Forsythe test. So since our P here is less than 0.05, we are telling that we did not satisfy the assumption of one-way ANOVA, so which also tells us that we cannot report the result of ANOVA. Instead, in place of that, we will be reporting Brown-Forsythe result. So let's move below for a while. Okay. So let's again continue our discussion by highlighting why we are telling that the Brown-Forsythe test will be used and not the ANOVA result. This is the ANOVA result. This is the ANOVA result and this is the Brown-Forsythe. So P is, again, as mentioned, it is less than 0.05, telling us that equal variances not assumed. So since equal variance test is not assumed, appropriate test is Brown Forsythe. So this will be reported. So Brown Forsythe, degree of freedom is 2 is equal to 5.948 and P is equal to 0.007. So let's clear this. Now let us decide whether this is telling us that there is a significant difference or not. So since, again, P is less than 0.05, this means that we are rejecting our HO, and HO is telling us that there's no significant difference. So we reject HO, then there is a significant difference. But it does not end there yet. So since the result is there is a significant difference, our problem is how will we determine if, let's say, the second child or the first child is significantly higher than the at least third child. So how will we do that? So let us, of course, clear our So since our P is less than 0.05, we reject HO and we are telling that there is a significant difference. It means that further test needs to be conducted. And that test would be the what we call as post hoc comparison test. So in using post hoc comparison test, we will be comparing the mean for first or only child compared with the second child compared with at least the third child. So going back to analyze, so we will go back to analyze. Analyze, compare means, and one-way ANOVA. In case that the result is not significant, there's no need to do this because anyway, if it's not significant and there's no significant difference, so why do you still need to compare? Of course, you cannot or you are not required to do that anymore. So analyze, compare, one-way ANOVA. And in the post hoc, you can find tests for equal variances assumed and tests for equal variances not assumed. Remember that the result that we reported is Brown Forsythe because equal variances not assumed. So we have here several tests that we can choose from. So Tom Haynes, Danetz, Games Howell, or Danetz C. So we can actually check all of this, but you are of course just required to choose one. Continue and okay. So since we did not, we of course don't need other results anymore. Anyway, we have all of this already. So here we can see the result of Tamhain, Danet T3, Games Howell, and Danet C. So you can just choose, but if you want to explore if there's difference in the result, then you can do that. But remember, if you will, of course, do that, uh, you can see here that you have similar result. Like we have, of course, to focus on the asterisk. So the only significant, if we have asterisk here, or if we will be looking at the p-value, those with less than 0.05 or which means are the ones significant. So this is significant. It's less than 0.05. It's less than 0.05. It's less than 0.05, less than 0.05. and it's less than 0.05. So these are the significant results. So focusing only on one particular test, for example, Tamhain test, the only one with asterisk is this, indicating that when we compare first child with at least third child, so the result is significant. But if we compare first and the second child, it is not significant. So going back to our descriptive statistics result, let us see here. So we have the highest value is the BMI of the first or only child, followed by the second child, and the last one is at least a third child. So we found that the result is only significant when we compare first and at least third child. So this means that looking at here, so this means that this is significantly higher compared with at least third child. But the first child and second child we have the same BMI. So they're not, what do you call this? The difference is not significant. So this ends the lecture video. So thank you for listening.